Oh, she came in right as I hit record. Hello, everybody. So, I'll wait until where mic comes on. Looks like it's on now. So, I guess tonight we're going to pick up where we left off last week. I don't think I said anything last week, but this is a lecture that I always get really excited when we get to because we're going to continue on with the persistent data, saving things, and it starts to feel like, I don't know, always feels like one of the big steps, right? When we get to all the formatting stuff, like we were talking about last week, the standards for saving our data, XML and JSON, or CSV and JSON, and we ran out of time for XML, but ready to transfer data from our software to another software, or when we're to the point that we're ready to make things big enough, we have to save the work so that people can go do something else and come back and finish it later. It always feels like a big step in the software when we hit those points. It's one of those points. So I was excited about that. Another thing I wanted to share with you all, last Friday, last Friday, I went to a meeting in the morning about this class as part of the curriculum committee, and the new SDEV 220 shell. They did something that I was really happy to see, and well, they did a whole bunch of things I was really happy to see. You all have probably noticed that going with the statewide course shell here, like I like to do. This one was set up before the most recent version of SDEV 140, which I'm pretty sure everybody in here took. It doesn't seem like we've gone much further here. And a couple places, it almost felt to me like the statewide course shell took a step back from what SDEV 140 covers. So the new version's much, they addressed a few things. It looked really nice. And one thing I wanted to mention, y'all might remember at the end of the semester, I went back and forth a couple times trying to decide on what graphical user interface package to use. And we just use that regular TK. It's a native package. It's in every install. Has some advantages. So settled in on that, and there were some points that needed made up. I added another GUI assignment that, along with the TK one, was just to kind of search for your own, through the ones that are out there. And the normal checking things out. Just go to Google, look at the 5 best, 10 best of sort of lists, and see which ones you kind of like. And in the new version of this course for SDEV 220, that I think is going to start in the fall or in the summer. I have a copy of it, so when I'm teaching this class in the summer, so I'm probably going to go ahead and use the new one. But they were using Django for the graphical user interfaces, which has a few things very useful, but it's primarily for web-based apps. So I thought that would be a really nice one. So I wanted to point that out to you because I don't think anybody's turned in that assignment yet. That was making up for those author companion site quizzes because they didn't put codes in the free version of the e-textbook, but they didn't put the code in the e-textbook, so we had to replace those points. So we're looking at a new one. Django's a framework for working with Python on web-based apps. So it would make a web-based application in Python. So that might be a good graphical user interface framework to look into. A very useful one was what I was thinking. I was like, oh, why didn't I put that on the list of suggestions? So whenever you go to work on that assignment, that might be a good thing to look into. You can just search Django and it's right at the top. It's a very popular thing. The pictures here. I was expecting pictures, but it would be put your graphical user interface on the web, on a web page for some cloud-based application sort of stuff. A very modern feel to it, so that's what I thought would be very useful. It seems like there's been a huge trend moving that way over the past few years. I do most of my stuff on the cloud, so That popped in my mind, and then let's see, then just a couple things on tap for tonight. Again, that the lecture that started last week, I'm always excited about this one because it's one of those points that feels like a step forward, a big step up, right? Like we're moving along and things are advancing, and then there's a few points in software development that when we hit them, it seems like it's suddenly a big step up. It's not just the normal slight step up. And storing our data or transmitting our data to be received by another piece of software completely unrelated to the one we wrote seems like a big step up. So we looked at a couple of the standards last week, CSV and JSON, and we kind of ran out of time. So I guess we can pick up where we left off. Probably a good thing. Is there something in the chat room, or was, yeah, that was from the other. I saw that on the other computer. So I'll go ahead and share my screen on this computer. I'll move the camera back over where it normally is. I'm standing over here. But yeah, I just wanted to suggest that Django thing as far as something to look into. And you don't have to dive super deep into it for that, because that assignment was just about a graphical user interface. So as simple as you would have done in any of the other graphical user interface packages, Django might be a good one to look at. Let's see. I think I cleared out my delete folder, so I probably don't have. I don't see the one for this class, so I better grab the files from last week. All that normal stuff we've seen before. Just working with the repository. Here, remote and origin. There we go. Should have it now. Oh, I don't remember what I called last week's folder. Choose class 1, class 14. That's probably not it. Transfer data, that's probably it. Oh, yeah. So here's what we were doing last week. So we created a simple object, a simple data type, just to test up with. Name, age, and town, just simple data about a person that we're going to pretend like our software works with. And then we use that to create an array of objects, or a list of objects, and then we wrote some to a CSV file. Comma separated variable, but we can determine what delimiter we want. That's the name of the parameter. When you set up the CSV writer, just you can add in an argument to fill the parameter, delimiter equals a space or a tab or whatever symbol you want to use to separate your data. The comma is just sort of a common one. And that's a format that usually works with spreadsheets. Spreadsheets evolved down to CSV files. So by default, they open with spreadsheets. Let's look at JSON, JavaScript object notation. It's the key value pair data structure for JavaScript, which is one of our languages that is officially listed as a standard somewhere. and it's really easy to work with. It looks like a lot like a Python dictionary if we look at it, but it is all in Unicode. And until we go passing functions, it looks just like a Python dictionary. I guess I should write something in there. So like in a Python dictionary, which we might get to this evening, that's probably going to be Wednesday though, we have that same stuff. So all of this would look pretty much exactly the same. But the difference between Python and JSON is if we needed to pass a function. So maybe we had a find some function, I don't know, say hi, just a hello world thing. Hello world. That's good for the example. So we have this function. If we want to pass it in a Python dictionary, we can only pass the reference to that. So we could only say, we could say, put a key up for a function and assign it that reference, pointing at that, the reference that points at that function. And then at some point later, we can say, ask for our dictionary, say like that dictionary, our function index, oops, and then add our parentheses on, and then that's where it runs. JSON's a little bit better because in JSON, we could actually pass the function in. So just hypothetically, say we have a JavaScript function of the same name, we could go ahead and pass that entire function, parentheses and everything in it. So then when we go and refer to that index, which JavaScript allows for numbers and key value pairs in JSON, the function's ready to run when we index it. But until we get to that point, if we just look at it, it's going to look like a Python dictionary, which is a really nice thing to work with. A lot of people like the key value pairs in our indexing. Our indexes all have meaning. We don't have to remember that our most important piece of data is an index number 3. It actually has a useful name to it. We're going to talk about dictionaries this evening. And JSON is just sort of the standard one. It doesn't necessarily happen with Python, but in most of our programming languages, those key value pair ones, the biggest advantage of that sort of data structure, which I keep using that word, but the formal definition of it is coming on Wednesday, is what I'm expecting. The short version of it is that database is long-term storage and a data structure is volatile storage. Basically the same thing. It's how we handle and organize our data. Database for long-term, that's what we're looking at this evening, and data structure for short-term. But those key value pairs, not necessarily in Python. Python doesn't play well with others. Python does its own thing, a little bit different. That's why, it's still written in on here from last week. If we want to turn a Python string into Unicode so that it works with everything else, it just has regular Unicode, we put a B in front of it, and then it just makes each one of those characters, instead of a Python string with all those functions built in, is just the 16-bit Unicode data. That is another one of our standards. So Python dictionaries don't necessarily work that way, but most of our key value paired structures, that's the one that can leave our software and load directly into another software. Because you could think of it almost like an array that brings with it its own index. It doesn't need reorganized stuff. It carries its own index with it. So a very useful data structure. A lot of people like to work with it. If you have unstructured data, it has an advantage over CSV files. CSV files it's what evolved into spreadsheets. So you think about those rows and columns on a spreadsheet. You want to fill up a nice little table looking spot in that spreadsheet. So you want structured data for your CSV, which basically means you would have the same data about every object in your database. And obviously you can do that with JSON as well, but JSON, if we're looking at unstructured data, JSON has an advantage over structured data, over the CSV files for non-structured data, which should be kind of obvious. The JSON isn't going to be loaded into like a table with rows and columns, so we don't have missing columns and spots. Those are a couple of our standards. The third standard for transferring data for other things to work with is to use a markup language. I think everybody's required to take the HTML and CSS class. Which, if you take that class with me, which I know a couple of y'all did, I always use that as an introduction to markup languages because we use them all over the place. They're efficient for the computer, yet still easy to work with for a human. Most of the time when we improve efficiency on the computer, it gets exponentially more difficult for the human to work with. Or vice versa, if we make it easier for the human, it exponentially decreases the efficiency of the computer. That drawback of Python that makes it a little bit slower. Because everything about Python is to be easy for human. Markup languages make the nice middle ground there. It's good for both humans and machines. And it's all stored as Unicode. So that's one thing that should already be anticipating when we get a few lines from now is our regular Python write function is going to try to write Python strings, but markup languages have to be Unicode. So we'll make that adjustment. We'll see that here in just a second. Basically, the main reason is it's another one of our standards. So whenever you're making pieces of software, you're out there making software, if there's going to be any need for your data to be compatible with other software, you're going to keep those standards in mind. Or if you're making some software that there's already alternatives out there for, keep these standards in mind as an import to your software. Make sure you give the users that import button so that they had a version or a similar type of software they used previously and stumble across yours, then they're going to be really happy because all their old files will import in as one of the standards and they don't have to redo all of their old work. Makes it a lot easier to transition to your software. So that the input on these is as important as the output. That's why I call the file compatible, or the folder, I call it transfer. And our library for this, there's a couple of them, so we'll need the whole doc thing to get into the whole directory. So in the Python installation, there's a folder called XML, and inside that is several different folders. Document object model, for those who've had HTML, or that word might not show up till JavaScript. Document object model, E-tree, parsers, and SACs. Those are both things that have a whole lot of pre-built filtering and parsing things for working with markup languages. I prefer to work with SAX myself, with SACs, but I can't really say that one is easier than the other. I've worked with SACs more than the other, and I think the main thing is it's one of those libraries that when I stumbled across it the first time, it felt like whoever made that library named things the same way I did. So it made it a whole lot easier to keep track of what's going on. But all of them have both of our features. These last two, those are more for reading data in. So like RSS feeds, really simple syndication is what that stands for. It's generally just an XML, a file of XML data transmitted across the internet. You just grab it if you want that data and then format it nicely. You may have heard of those. One of our standards for getting data out to the world. For our example here, I decided to go with E-tree because that's what we're working on. And one of the biggest advantages of markup languages, it's hard to see when we look at the text file, is that it is a tree. Markup languages are a tree structure. So we saw classes, right? We have a class, and then we'd have the child of the class, and sort of a hierarchical sort of thing. One of the big ones we're going to talk about soon, we've already seen this picture a little, is tree structures, where we have nodes and branch those off. And then each branch is a child of the node above it. That's probably enough for the diagram of the tree picture. So another advantage of markup, the main advantage of markup languages over JSON or CSV is that it's actually a tree structure, which we're going to talk about. That's one of the big things to talk about here before the end of the semester. I think it's like near the end, module 6 or 7. But each node is a parent of every branch and leaf on that comes off of it. And each child is, or branch, each branch and leaf is considered a child of the node that it branches off of, which is one of the standard, really good ones for you to work with. Which is why we're going to spend an entire night, maybe 2, talking about trees in particular. And it's hard to see when we look at the text file, but markup languages are this style. So when we export that from our software and bring it into somebody else's software, or somebody else exports from their software in XML, we bring it into our software, it comes in as one of our best data structures. It's probably the best thing about one of the best things about markup languages. There are a lot of advantages to it, I'm sure. The biggest disadvantage to it is writing all those tags. For those who have had the SDEV 153 class, and actually typed all those tags. But that's why we have libraries like this one right here, because this will write all the tags for us. So we just have to say what our data is, and then it'll do all that tedious writing the tag, adding the tags to that data and writing the text file. It'll do the tedious typing for us. And that takes away the biggest disadvantage of it. So in that library, there's an object called elementary. Well, there's several. We're going to look at tree. And I'm just going to call that ET. So that's the one we want to import. That's the easiest built-in one in Python to work with XML. Yeah, then we just tell it what tags we want. So here we do kind of need to think about the tree structure. You might not have thought about that at all when you were doing HTML for this SDEV 153 class. But that terminology is what we're actually making, so it's good to have that here. So I'm going to call the first one root. I was already thinking ahead. I want the tag to say people, but as I think about a tree, I'm going to call that very top one root. And on our data, just to remind you, let's scroll up. Our sample data was this array of those person objects. So that's going to be our root element, our root tag, we'll call people. So that element tree, we can say dot element, and I'm just going to okay, yeah, the particular text box there has some useful things on it. So the very first thing is what is the name of the tag we're creating? For those who have seen markup languages before, we have that opening and closing tag. What's the name we want on that? In this case, we'll do people. that matches our array. Union stuff, that's getting into more advanced tree things. The attributes, you can see just pass it in the dictionary. So for those who have seen markup languages before, we just pass all our attributes into this tag as a dictionary. I'm going to come back and do that after we add put all the tags in. So I'll do that as a secondary thing, just to see the syntax. And I will see the other one on the list. The thing that goes in between our tags is just text. And we'll access all of them that way. So there's our root element. And now we need to add things to that tree, which kind of is jumping ahead. We're going to spend quite a bit of time talking about trees. That's one of our most important data structures in computers. I guess for now, you might just have to take my word that that's one of our most important data structures. We've seen that picture a couple times already, even though we haven't got to it yet. But we want to set up a tree. So we need to add some branches to this. So I'm just going to loop through that array. Actually, I'm going to do two things in this. Because one of the things that I'd had in mind for that task management software was the filters. And one of the things that I was thinking that people would probably want when they set up the filters, like how difficult is it? What I was saying is things like how difficult is the task? Put a skill level attribute in all of your resource objects, or at least the people resource objects. And then when you're filling out a task, it's going to be a really hard task to make sure they have a skill level of at least 3. Or if skill level is greater than 3, add them to the list. Make sure they're the better people working on a particular task. Those are things I was thinking of and counting, but I realized afterward, I think when we were talking about it after class the other day, when I typed it on the screen, I suddenly realized, like, oh, I don't think we talked about this yet. I meant to talk about it earlier, and time got away from us, I think. So we'll see how to count while we do this as well this evening. I might have typed it very quickly last week, but I'll actually talk about what I'm doing as we do it this time. But we'll come back and add that in. So first off, we're just going to loop through there and write all our tags. So we have our root node. So the thing that comes off the root, when we're talking about tree, would be a branch. So I'll use that word here. So we'll make a new branch. Again, we can set up from that element tree library. And there's element, or if I scroll down the list, I start typing. Oh, no, it's not going to show up. There's element and sub-element, which you'll notice has almost the same parameters, except for one other that should look familiar after doing the TK stuff. You might remember I drew this picture a lot when we were going through the TK interface package. And all of our widgets, we have that top level thing, or the kernel, the root thing, the main TK object, and then we would attach other widgets to it, and then nest other things in there, and kind of form a picture like this. We do the same thing with our XML data. That's how it's structured. So we have to say what the parent element of this one is, which as far as markup languages means the text is going to be nested inside there. That's why it's hard to see this picture from the final formatting in Unicode. But this is going to be a sub element of the root, or a child of the root. And our first one was called names. We'll add that tag in. And I'm not going to do any extras right now. I'm going to come back and do attributes afterwards. I started to do it and then it started looking cluttered, so I thought I'd come back. Oh, whoops, that's not what I meant. Sorry, let me set I'm going to copy this from up here. So I'm going to grab a copy of this so I can point to it. There we go. That way I don't have to keep scrolling up there. So our root is this people structure that we stuck all of our person data into. So the first child of that is person. Then as we go through, we want to stick these pieces of data inside that person element. So we'll add another branch to it. Or there's a tree drawn on the board, so and since that's going to be an important thing coming up, I suppose I could just put the labels here as part of a way to introduce trees. So we have our people. We don't have multiple types of people. In our case, we only have one type of person. No discrimination in our data today. And then each one of those person has 3 nodes off it. Has a name, an age, and a town. So that's kind of what our tree looks like. And to jump ahead a little bit, the big advantage of this, you might remember when I did that quick picture on the SQL database, relational databases, we have a table. We have a couple tables actually. And the advantage of a database is like maybe this field and this field are actually the same. So instead of reading all of our data, like we would for a JSON file or a CSV file or a sequential text file, we can use that relationship. So if we're, say we know this piece of data, we can just follow that a couple columns over in the same row and then follow that column over to our other table and get to any piece of data without knowing the entire database. We use the relationships. And the same thing happens with trees here. So that's why it's such an important data structure. This one happens in long-term storage and this one happens in RAM. So it gives us that jump around ability in RAM. We don't have to know everything we have in RAM. We can use the lines, not just the circles, those lines are connected. Might be one way to put it. So inside our person, each one of our persons is going to get another branch, or really a leaf, to stick with that terminology. So I'll say leaf 1 is going to be another sub-element, and this time our parent is the branch. And our tag will be name. And I'm going to do the attributes separate. I'm at the attributes in a moment. Then we have leaf 2. There's a sub-element here. Again, it's a leaf on the branch that we're currently creating. And this one will be age. Leaf 3 is sub-element branch. That was the third one. Suddenly was drawing a complete link for a second there. So that sets up our elements. Then we want to store them somewhere. Now we'll put that root, all the branches we create, and we're going to do a loop. So each one of those will be a separate branch. Each pass to the loop. It's going to make a new branch and then stick 3 leaves on each branch of the tree. So now we're ready to build the whole tree. So we'll make a data field called tree, called ET element tree, I think. So instead of an element, we want to make the whole element tree now. And all we have to do is say what the root of that tree is. So obviously I was using the terminology is how we want to think about this picture with our root, then our branches, and then the leaves on the branches. Hopefully that makes sense. If we added more things here, write a couple more things off of this last bubble here, just on the terminology. Maybe added a nickname. Now, instead of a leaf, this one would be a branch, and that's the end point is the leaf. So hopefully that terminology makes sense and doesn't require a whole lot of thinking. Nickname was what I had in mind for an attribute to add on that here in a second. So just some terminology things because it's kind of an important one to deal with. I guess we could print that out and see what it looks like. This does not do pretty print. Oh, well, it just tells us we have a tree. I guess I have to put things in it. Yeah, I'll tree one. Oh, whoops, did I mess something up? Oh, I have to ask for the root. Tree root is tree.getRoot. I guess I could print root. That would do the same thing. There we go. We got a little more information about it. It's an element, where it's stored. They tell us what the tag name is. We can move through there. I guess I'll go ahead and write this to the file. That's what happened in the example. That's what we're really talking about here, doing that file. But we can access it in that tree structure at this point. If you just want to set a piece of software up to work with that, because it makes sense to have everything organized into a tree structure. That's one way to get a tree structure right there in your software ready to work. For us today, we're mostly looking at writing files, right? With open, I don't know, data file 1.xml. For writing, only this time we had a restriction. XML does have to explicitly be Unicode, not Python strings. So instead of just W, we want to put WB for our mode. We want to write binary, which when we say binary on a string of Python, it automatically converts it straight to Unicode. By default, obviously we can change that. We're programmers, we tell the machine what to do. The default is if we say binary, it converts it right to Unicode. Obviously we have the power to change that like anything else in the language. So we'll write binary as, I'll call this XML handler. And then it's a little different than what we did before, because before it was a lot like, well, I guess we didn't really do anything like the sequential text files. The sequential text files, I believe everybody's already saw that write method before. In our CSV, we have specific write row methods. In our JSON, we had the JSON dumps and JSON loads. So they came with particular ways to write them. And we do the same thing here, except that it always seems backwards to me, but I guess not. We'll just say tree.write and then pass in the handler. I'm not sure why that feels backwards to me, but maybe the sequential files or something that regularly shows up. Think about doing the handler.write, but here we're doing our tree object.write and tell it what handler to use. What file handler? Oh, which I put the wrong handler in there. Call that XML handler. There we go. So that should create our XML file. Uh-oh. Just a little typo. I left the D out on the line above. I had handler or something. So fix that typo and try that again. There we go. No error messages. So we go look at where this folder is located at. Oh, actually, I can open it right here. There it is. You can see here in Spider, we got a different icon, an icon that looks like the little markup language tag. Indicate what it is. So if we open that here in Spider, the first thing you'll notice if you've worked with markup languages before is it does not do pretty print. That's actually what we call it. Some libraries have an option where we'll actually fill a parameter, pass a boolean into a parameter called pretty print, and then it does the line feeds and indents and all that nice stuff. What I usually like to do with these, since that's a built-in one that's easy to work with, if we open an XML file in a browser, the browser will automatically convert it to pretty print. So come over here where it's stored. I guess it's this one. Oh yeah, the XML document, which stands for Extensible Markup Language. I can't remember if I wrote that on the board last week or not. But if we open it with one of our browsers, they will automatically do the pretty print. Also in a browser, you can kind of see a little bit more of the tree structure where it expands and collapses. Because like our root of a people, we can collapse all the children of a particular element. So a branch, like our person branch, we can collapse all of those leaves or other branches that are inside of that one. Give a bit of a hint, but that's kind of what it looks like. Oh, whoops. I just realized I left something important out there. We probably want to put our actual data on there somewhere, don't we? At the very least, you can see that it writes the tags. So it wrote all the tags for us. We just forgot to put the data in there. And that is just a data field we can access on it. So like leaf one. Oh, well, there's the three main ones. Tag, tail, and text. Tag is the tag name. Well, we already set the tag name when we created it. So the text attribute is our actual data. So p.name. Leaf2.text is p.age, which is a number, so we need to turn that into a string to write it to a text file. And same thing on top. Leaf3.text is p.count. All right, sorry about that. Hopefully y'all were probably looking at that wondering where our data was. Like, should there be some data, some actual data involved in there? I was thinking too heavily about write the tag parts, which for a short example like this, it wouldn't take much time to write those tags. But if we have hundreds of data points or thousands of data points, that's a lot of tags to write, isn't it? That'd take forever. But if we can just do it as a loop, it goes a lot quicker. So let's run that. Now, if we look at the XML file, there we go. You can see our data showing up in between the opening and closing tags. For those who haven't had markup languages before, I know most of the people in the class have already had it. It's required at some point. We have what we call an opening tag and a closing tag to single out one of our data elements. And in between those is the text form of the data itself. That's the general format of a markup language. We can also put some essentially metadata about it in the form of tags. So inside of our opening tag, we can put some background data about that data. So what I was thinking is just like some nicknames. So I'll add those here. So to make it match. And to look at that thing that I thought we already had seen, but had not. I'll make a list called nicknames. Can't seem to spell today. So let's see, our first one is Charlie. So I don't know, I'll call him Big C. I don't know, Sal is the first thing that pops to my mind when I look at that name I made up the other day. Alan, that makes me think of Alien. So I look at that name. I don't know, I'm just gonna say Elf. I was looking at the name, trying to think of a nickname. And I was like, all the people I've ever met named Jeff, I don't think any single one of them has ever gone by a nickname. Most of them even seem to prefer to spell out the whole name. They don't even go by Jeff. They go usually by Jeffrey. But making up some nicknames. So say these people do have nicknames, and we want to include that. So it's not data on itself. It's connected to our name data. So we can add that in as an attribute. And it looks just like the text. So leave one, which holds our name data. We can add this attribute, which this one has been here since the beginning of Python, so it's abbreviated. Lately, we've been looking at a lot of things that are spelled out all the way, but this one's been here for a long time. So the abbreviation of attribute, ATTRIB, and we'll assign that something from our nicknames array. And now we're up to that other point I wanted to look at. Because well, here, our arrays aren't quite parallel. Right? If we've worked with parallel arrays before where we line everything up, but the nicknames go with the a subset of what's in that other array, not line up exactly with the other array. So we need a way to get the indexes that match. So like our first one here goes with this object, or our third one goes with this object. And a useful way to do that is to double up this list we're walking through. There are multiple ways to do it. An easy way to start is we have a built-in function called Enumerate. So we don't want to just walk through the people list. We want to walk through enumerating the people list. So along with walking through it, we want to count while we do it. We want to count which one we're on as we do it, which we'll need to put someplace, and that'll go first. So I'll just, so as we walk through, we have two variables to fill in now. We have an integer, let's use I for integer in this case, which one we're looking at, and P is the list itself. I guess you could get a similar thing by walking through the length of the range of that length. I think that's how most people would do that starting out. Let me put it up here. So for P in range length. I'll use the I there because I've got it. For I in the range that goes the length of our people array. You may have seen something like that. A lot of people do that starting out. Enumerate basically does that. Only we're still walking through our list. So we can just refer to the items in the list or whatever iterable we're going through. Maybe it's a file, a set's the next one we're going to look at. A few different things. Anything we could walk through, look through folders and stuff like that. We'll see that. I was hoping to get to it Wednesday, but this is taking much longer than I thought it was going to. I've gotten used to the 4-hour classes. 2-hour class has been throwing me off. So I will be our number as we count our way through, and P is the element from that list itself. So then when we want this to line up, we can just ask for that I, the current integer that we're counting to. Because I could use count or something there. That might be more useful. Count. And yeah, that's a more descriptive term. So that way we're counting which one we're on as we go through it. Whoops. That has to be a dictionary. I got distracted. Whoops. So we need key value pairs. So that's our value, and I'll just call it nickname. So our attributes, for those who have worked in Markup Language before, they just go in as a dictionary. I think I already said that and then forgot to type it. We've been in too big of a hurry here this evening. So no error messages. And I'm just going to look at it in the browser because it looks a little bit nicer that way. There we go. You can see we have attributes in some of our opening tags now, which is essentially metadata about that data we're storing. So on the tree picture, it's like we have some stuff here. Like we made this leaf a little bit bigger and then added that nickname data field inside of it. Reading that back is really easy. So just open data file 1.xml. And well, when we wrote it, we're gonna have to open the file. I was thinking of a different library. We can just put that right in a tree. I'm gonna call it new tree. That way we know it's something different and not referring to the previous one. I'll just make a new tree, and that's going to be our ET library, the element tree library. It has something in it called parse, which I believe y'all have probably heard that word by this point. Parse means to read through a string of data and find the parts you want. Sort through a bunch of text and look for the parts you want. So we can just do that right here with that file name, data file 1.xml. And then we can grab the root from it. I'll just call it new root to keep it separate from the other one. Is new tree.getRoot. And then we have the picture here. All of our other stuff is just children of that root, and it comes along with it. It's a tree. All this stuff is connected, right? If we grab the roots on a tree and start pulling on that, we're gonna pull the whole tree with us, right? Or really anything. If we grab a branch on a tree and start pulling that branch, the tree is gonna bend that way. A small tree would come with us. But it's all connected. So all we have to do is grab the root, and then we can loop through that root. As an iterable item, so we'll index it like we would an array, but it's a tree. So it's not a list like we've worked with before, or tuples. List and tuples are very similar. One of them can be changed, one of them can't. Dictionary, we talked about that briefly, so because we wanted to start using it. A set is like a dictionary without the keys. The order doesn't matter, the order will change on us and stuff. You should probably notice sometimes we don't need those indexes. We want the whole collection every time. So we can work with the stuff that we can throw out the part that does all the indexes and indexing and refers to a single element in there, because we know we're going to loop through the whole collection every time. That's actually the next thing on the list to look at, but I don't think we're going to get there this evening. But a tree, likewise, we can index all these things. There's better ways to walk through a tree, but indexing works. So for I in range, I'll just do length of the new root. Actually, I had a 2D array here, but I'm going to print this out first. I'll lead into that spot. New root I. Whoops. In range. Did I spell that wrong? Okay, so it's Python, so I'll try a lowercase r before I go look it up. But again, get through is one word, all lowercase. And you'll see when we print it out from like it was a 1D array, what we got is a bunch of the person elements. But we wanted the stuff inside of those. So those are elements in a tree, so we can index them the same way. Oops. It's different. It's completely different than a 2D array. It's indexing the branches on our tree. So here's the first index. Here's our second index. But it's when we're writing our code, I guess we can think about it that way. So we'll walk through that one. So range the length of new root, whatever element we're looking at. And then we want to print the ij. Which you already noticed if we say print, that's just going to give us the elements. We probably want like the tag name. So print dot tag plus I don't know, maybe a colon plus new root the ij new root with the text attribute. Some of them have attributes, so I'll go ahead and print that. New root ij attribute. Oh. We're making all kinds of mistakes in Python this evening. Hopefully that makes sense. So it's different than a two-dimensional list, but we're going to treat it as a two-dimensional list, or similar to a multi-dimensional list. Is here's our root. Then here's that first index. And we have 3 things in that first index, and then we can continue that on. Every branch becomes a new index, and then usually we'll want something like our tag name, the text that's in it, and then the attribute that's there in order to tell what to do. So there we go. So in the tag name is something called Charlie. His age, where he lives, and then his attribute nickname in this case came back as a dictionary. So it gives us that nice structure to work with. And then, like I was saying, the advantage of a tree structure is we don't have to worry about all that at once. Which is one of the things I was explicitly saying that's not like a list. Because in a list, it's iterable because we have all of it at once. The way a list works is at the end of each element in the list, we add on a pointer that points to the next element. And when there's a null pointer, something that points off to emptiness in the RAM chip, that doesn't point at anything, that's how we know we have the end of the list. So with a list, we have to work on all of it. But with a tree structure, we would index it the same way in our code, but we can use these connections to bypass large chunks of the data. So it makes it a really nice data structure. And that's our 3 primary types of data for compatibility. So I put that name on the file. So we can work with other software. Those are the 3 most common ones. So I want to keep that in mind for both the output and the input. I also made a note here in my list to look at the Python docs on the E-tree, XML and Python. Because there is a few more things there. So if we go to the Python docs, y'all know where the documentation is. You see a lot of the stuff for reading things back in. When I went to look at it, it's really about halfway down here, I think. Yeah, so we have some built-in methods that are really, really nice for that. Built in such a way that methods for parsing the tree were made in such a way that they go directly into the form and we're iterating through. So when we have that markup language there, our data in markup language form, we can do that root.findAll and add in a bunch of really some nice filtering options as part of our loop. Or that very first line, we've looked at constructors or comprehensions and generators. So obviously that would work very nice for, say, a comprehension or a generator to put that stuff into a list that's going to stick around. So we have our XML data over in some text file on the hard drive, and we just use this find all method in a list comprehension to bring the parts we want right into a list to work with. Different ways. There's a lot more we can do with that, just sort of introducing it here. It gives us that nice tree structure, which is a very powerful structure and a useful one to work with. But the biggest reason I was bringing it up is the compatibility issue. So we can work with others. Then our local storage, what time is it? 7:05. Sometimes we don't want to share our data, right? When we save a file, it's saved so that we can work with it in our folder, and we'll just stick it in our software alone, and we'll stick an export button in the menu. So if we need something to work with other software, we can just export the file in one of the standard formats. So we have a couple ways to do that. We saw Y'all have seen sequential text files, they'll show up in the previous class. I'll use the same data and try to sort of move things along quickly for the next one. Oh, I guess I better uncomment that. So sort of the same data, which leads me to from person, import all. I'll make a unique one to individual. It's a person. Becky, age, from so I have a counter around here. Or couldn't think of any nearby towns for a moment there. So that gives us some data. Another useful one, there's also sequential files, but when we work with a computer's working with everything in binary. Right? So the computer's working with that and RAM, the registers, the CPU grabs things out of RAM, moves them into the registers to do the full adder to carry out the current, execute the current step of the instruction, and it puts it back in RAM or sends it back to storage. It's working with binary the whole time. So we have to make an adjustment to get to text. So an alternative to a text file is we could just save a binary file. We talked about these the other day. Python, when it was created, they named the module for writing binary files with a common verb that is no longer commonly used. Back in the day, the standard term for moving binary data directly to storage, putting in a format that would go directly to storage, was pickling the data. That was one of many things. And when they put Python together, that's what they called their library, was pickle. So, but that didn't really stick around. So most every place else in the modern world outside of Python, you will see the word serialize. I'll put a comment in here. Old verb, not used anymore. We typically say serialize. I think I had trouble spelling that, but yeah, there were multiple verbs back in the late 1980s, early 1990s. But serialize is the one that ended up sticking around. But when they wrote Python, they used pickle. It's just like writing a text file, so and kind of jump ahead a little bit, nothing too fancy here. We'll open one. I'll call it data file 2. I need some extension. Your textbook probably uses DAT for everything. You're supposed to stand for data file. But there's something on Windows systems that are called DAT files. So if you give it that extension, you give it the .dat extension, a lot of your Windows machines will will want to do something with that file. So textbooks always use .dat for the data files, but that's not a very good extension to use. Make up something arbitrary related to your data. There's been so many file types, there's a good chance that when you come up with like a 3-letter combination, it's already been used somewhere. Obviously, there's some ones you want to avoid, right? Like you wouldn't want to call it a .doc, because that's one of the most common file types. You wouldn't want to call it a .pdf, because people would look at it and think they know what it is. But it would be something different. Or you wouldn't call it a .jpeg. So there's some that you know to avoid, but And there's so many out there, you just kind of have to pick one and go with it. I guess that's why textbooks went ahead and started using DAT all the time. It's like, oh, there's so many out there, it's hard to avoid them. So I as well use one that makes sense for data. The biggest difference over the writing sequential files is something we've already seen. We don't want to just write a file, we want to write a binary file. So WB as I'll call it bin handler. That seems a good name for it. And then we'll use that pickle library and call the dump method. The other day when we were looking at the JSON one, I paused to very explicitly say with JSON, we want to use the one with the S, the dumps, and it's not plural. For pickle, dumps is plural. If we have lots of data to dump, like a big collection, we use dumps. But we also don't really have to do that much. Oh, sorry, the distraction. Those messages that keep popping up in Teams are about cryptography class. Some new people in the cybersecurity degree were interested in that. And I was like, seems like something we would definitely run, but I don't know the number. And I couldn't find it from the search engine. So, which might be an interesting thing if y'all need another SDEV, like apparently saw that last message pop up. SDEV 245 is cryptography. So about encrypting data. But here we're just storing data. So no matter what we have, we're turning it into a long string of binary. So we can pretty much always use the singular case here. So I'm going to put that whole array here. So pickle.dump, no S this time, no S. People. Know what I want to do? Yeah, I'll do that first. And then we say what handler we have. Which will be enough to write our file. So I'll read it back so we can see it. So again, with open data file 2.per, I just made that up to match a person. And this time we're going to read binary instead of just read. I'll call it bin handler again. That seems like a good name for it. And it's pickle.load. So just like the JSON one, in JSON you want the S, you want dumps and loads. But with pickle, you want the singular version, no S. So dump and load. And if we're loading it, all we need to say is what handler can see it, which one of our file handlers can see it, but then we need to put it somewhere. So we'll stick it someplace called stuff, and then I'll print stuff. Oops. Oh yeah, that was right. Hadn't saved yet. Yeah, I don't know what to call it. I was called store data. Couldn't think of a name quick enough. When I run that, do that. Clear that. Clear the old stuff. Now when I run it, it looks funny because we only see the reference. Right? But I'm guessing at this point you all have seen those references might show up. So you know what that's referring to, right? There's a person object at some point in memory. That default version of that's what happens if we don't do the string method. Although I thought we did the string method. We did the string method, so it's just pointed at it. You can see we have this array and where it's stored. So we could refer to a particular one, so maybe number 2 on there. And that way we get the name from it. But our other data is still there. I'm gonna do .age, because once we get it back, that's just our object. You see, it just took those objects, send them right over to the file and brought them back. Nothing too fancy there. We can look at that file. So here it is. I'll open it with add. Maybe. Yeah. We'll open that up in our text editor. We'll recognize a few parts from it. So it looks like some of that made it in as Unicode. This person, object. Oh. Well, there's the person object in the person library. It looks a little more complicated than where we put that in our code and just said person dot person. Or there's some names. Name, age. It thought it recognized a K. I don't know what would be up there with the age and pound attributes that would be a K. So that's probably just the text editor saw 16 bits that looked like the Unicode layer. So we're in the right order to be a lowercase k. So it's like, oh, I recognize this, but it's in binary form. So the text editor recognized some of it, but definitely not all of it. As far as the size, that's the other big issue on these. Notice there's not much difference in size at all. We open properties, so it doesn't round. Is that close to the same thing? So storing it as a data, it says 1 kilobyte was 204 bytes, whereas JSON, probably what most of y'all are going to go with. I think a couple of y'all specifically, more than one person specifically mentioned in their final project they're going to use JSON. But you can see it's only four more bytes than the direct binary form. So not much change there. The XML is probably quite a bit bigger. It's still under a kilobyte, but 365 bytes. So it's still a really, really small file, but it's a whole lot bigger than the other two to store the same data. Actually, that did have some extra data. That had the nickname. That wouldn't count for 153 or 161 extra bytes for just those few characters that are there. So it is big. You can see they're bigger, and like we already talked about, that's one of the things we're going to start considering. How well does it accomplish the task we're looking at? Not just does the program accomplish the task, how well does it do it? So JSON doesn't really seem much worse than binary as far as file size. We can write stuff to JSON, read it right back in. Write stuff to binary, read it right back in. If we compare how we're doing that side by side, oh, well, that library allowed us to just open the file and loop through it. Then we read it back. We open the file and read it all back in. So nothing fancy there. One line each to write it. And if we go over to the other one, when we did the JSON, looks like we had to actually add a loop for the JSON one. So not much more work either. One more line of code in each. When we use the with and then a for loop, it adds one more line of Python code and 4 more bytes into the thing. So 32 bits. All our machines are probably 64 bits anymore. you're on a 32-bit computer, people might periodically comment about it being an old computer, right? So that's all we're saving between JSON and binary. And we get the readability, works with other stuff. So JSON's a really good one to work with. But these are kind of our standards. And you see, there's not much in any of them. Whenever you put a piece of software together, it's really not hard to add all three of these standards in. If you're going to have that so that it's compatible with other software, then you don't really need the binary one. Because you could just use that as your own storage as well. Use one of those as your own storage, and then add the other two in by an export button in case a user needs it. Store in a custom format. There are advantages to custom format. The more you customize the data, our objects are very simple here. So the more that you would customize your data type objects, the more useful binary files become. So it kind of depends on the software, but as your objects get more complicated, storage in a binary file becomes more useful. Then you have to do more to read back to the standards. There's one more that I wanted to look at, but it's going to take a few minutes. I want to make sure there's time to do stuff. So we've got around half an hour. So the last one uses relational databases. It's kind of like a binary file. It's particular to our software. I had some other stuff in the binary file, but there's nothing that would be different than what we saw there. I made that individual item. We can just write that as well to a binary file and then read that back in. One thing about a binary file is it's a long string of binary, so you don't want to split it up when you write it or when you read it. So it's pretty much always going to be one line of code to write. That's pretty nice. They all have different advantages. Still want to look at the SQLite, which is like binary. It's unique to our software and stays local to the extent the user doesn't select to put that file in the cloud, but local to the software we're running, and all the advantages of a relational database, which kind of is a standard, but using the SQLite library, SQLite library, it is compatible. You might remember that was one of the issues that SQLite pledges to be. So it goes to other software, but if you've worked with databases, I believe it's DBMS 110 class, you probably remember that you have to know the database. So we can't just send that file like we did a JSON file and somebody read through it and parse it automatic or parse it without having ever seen it like an XML file. They would have to know the database in order to put the queries together and work with it. So it's not quite as compatible. Their software could read it, but they wouldn't know what to do with it. Or they have to spend a long time figuring that out. But it does have some nice advantages. It's very, very fast, very, very efficient. That's why the structured query language and relational databases have been around for a while. They have a lot of advantages. It's a great example of the mix and match thing. We're doing this all in Python, but normally we mix and match things to take the optimizations from each one. We don't just pick a method and stick with that forever. We look at the situation and try to choose the one that is best for our current situation. Usually in programming languages, data storage, transfer methods, all of this stuff kind of adds up. And that's what we're really looking at the next half of this semester is we want to think about those optimizations. And all of our programming languages, including Python, we'll start doing this soon, have built-in ways to take measurements and see how it goes. Kind of what I just did here, where if we open up the property, oops, got renamed. Open up the properties on those two files. Oh, I have to do them one at a time, I guess. Windows 11 made that harder than it used to be. Open up the properties on all of our types of data storage. Okay, so there's 1, 2, 3, 4, 3, 4. And do that comparison. Right? It's not hard to look at those numbers and see which one is smallest, right? We can quickly look and see that one of those formats is way smaller than the others. It's a digit less than the other ones. $88 bytes versus, well, an XML file is almost 4 times the size of a CSV file. JSON and binary are comparable, but that's one of the considerations we're going to start. We need to start looking at. And our general term for that is going to be telemetry. We want to take telemetry on these storages, which basically means we're going to take measurements. We don't need a lot of fancy measurements. This one's storage, we can tell quickly which one's smallest. This one's not much bigger. To get I guess a second measurement to take would be a bigger file of each. So that would be my recommendation for lab time. If you're following along, double and triple your data size. So we had 4 things in that list that we wrote to those files. So make another one with 8 things and another thing with 12 things and see how that number increases. Does it go up linearly? So if we put 4 things in CSV file stored 88 bytes. So if we do 8 things, is it still 22 bytes a piece? Is it still going to be 176? Is it going to be 176 bytes? So that doubling the CSV file is still smaller than all the others? Or is there some overhead that comes with the increase? That's my recommendation for lab time, to start looking into those things. Increase the size on each of those file types we've looked at, and just pull up the properties and check the size to see what happens as our data collection grows or shrinks as a first step in telemetry, because that's an important thing so that we can optimize for our situation. The one we want to work with, the one that's easiest to work with, the one that's smallest to store, the one that's fastest to transfer, all those things matter. Looks like we got about 20 minutes left. That's my recommendation for the next 20 minutes to start into the telemetry stuff. I was hoping to do SQLite stuff and have 20 minutes to do that at the end, where the telemetry would just be add a bunch of stuff into the list and then run the same methods to a different file name so you can compare them side by side. An easy measurement to check and confirm, and a good start into this next, what we're doing the next half of this semester, the second half of this semester. Really. Does anybody have any questions about that? We'll get into the SQLite storage on Wednesday. Okay, I assume the silence means no questions. If you have any, let me know. For the next 20 minutes, I'm just going to be sitting by my computer ready to answer questions if you have them. Otherwise, you all have a great evening, and I will see you on Thursday. I keep saying Wednesday again. I'll see you on Thursday. I guess I'll see you. The rest of y'all, I'll see Thursday.